What's up? I'm Vin, and today I want to talk about the first derivative test. So here are some definitions that we're going to need to know, and let's get started. Now, before we look at some actual questions, I want to look at the concept of why the first derivative test actually works. So notice here that we have a local maximum, which I'll just abbreviate like this. We have a local max. And remember that the first derivative f prime tells you the slope of the tangent lines to f of x. So if we look at this local max here, notice we have a horizontal line, and the slope of that line would be 0. But this line right before the max has a positive slope because it's a increasing line, and then the slope right after this 0 slope here is negative because this tangent line is decreasing. So notice we have a slope change from positive to negative, which means f prime changes from positive to negative. That's why the first derivative test tells us a local max occurs when f prime changes from positive to negative. Now if we look over here at this local minimum, which we'll abbreviate with this phrase here, notice we have a 0 slope at c sub 2, but then right before the 0 slope, and I'll make that a little bit neater. So right before this, the tangent line has a negative slope, and then right after the local minimum, the tangent line has a positive slope. And remember, f prime tells you the slope of the tangent line. So f prime is changing from negative to positive when we're at the site of a local minimum. Now, the last one worth mentioning here is we have another local maximum. But for this one, this is the sneaky kind. Okay, now why is it sneaky? Because for this critical point of f of x, this is where the derivative is undefined. So notice here I could say that f prime of c sub 3, that this is undefined. And the visual confirmation is that we have a sharp turn here. But just know that you could still have a local maximum at a critical point where it's the sharp turn kind of critical point where the slope is undefined. And notice we have a local max and the slope is changing from positive to negative, even though we don't have a 0 slope at the top of this point here. We have a sharp turn. So for this first question here, we want to find the local extrema. So that's the local maxes and the local mins. Now looking at this picture here, we could just find it by looking at it here. Like notice we have one at x equals 0, and it looks like we have another one here at x equals 2. But let's say we don't have a calculator and that graphing just in general is not an option. Then what we need to do is we're going to find the first derivative, because what we want to do is use the first derivative test. So we're using power rule here, and we get 3x squared minus 6x. And then once you have the derivative, you want to find the critical points. So you're going to set the derivative equal to 0. So notice here f prime of x is equal to 0 when, and I would prefer to write this in factored form. This is 3x times x minus 2. So we could set 3x times x minus 2 equal to 0, and then this is going to give us, the first factor gives us x equals 0 as a root, and then x equals 2. So notice what we have here. This is starting to bring the picture to life, that at x equals 0, we have a critical point, a 0 slope, and at x equals 2, we have our second critical point. But now, if we're doing this without a calculator, then what we need to do is we need to make a sign chart for f prime. And the mark that we're going to make here, so let's just make this neat. So this number line, we're going to mark it at 0 and at 2 because those are the critical points. And now what you want to do is you could do this the long way. And the long way would be to actually plug in values on each interval. So notice from negative infinity to 0 is the first interval. And let's say I plug in a number like -1. So I plug that into the first derivative. And I would prefer to plug it into the factored form. I have 3 times -1, which is -3, times, and then I have -1 minus 2 is also -3. And then if we multiply those, that's going to be greater than 0. That's going to work out to positive 9. So on the first interval here, I can mark a positive. So now if we continue here, let's look at the second interval from 0 to 2. If I plug in a number between 0 and 2 into f prime, I'm going to have f prime of, let's say I use x equals 1. And if we plug that into the factored form, we have 3 times 1 is 3. And then we have 1 minus 2 is -1. Now the value doesn't matter. All that matters is the sign, and 3 times -1 is less than 0, is negative. So I just record a minus sign here. And now the last interval from 2 to infinity, a nice number to plug in would be x equals 3. And I plug this into the factored form. 3 times 3 is 9. And then we have 9 times 3 minus 2 is 1. And this is going to be positive. So that's the sign of our last interval here. And what I like to do is I like to record the behavior of f of x right above it. So if f prime is positive, f is increasing. Then if f prime is negative, our function f of x is decreasing. And if f prime is positive, f of x is increasing. So notice this function goes from increasing to decreasing back to increasing. But now, if we want to summarize everything that's going on here, the first derivative test tells us that when we have a sign change from positive to negative, we have a local max. So we could say that f of 0 is a local maximum, and the reason being that f prime changes from positive to negative at x equals 0. Now, if we want to classify the other point here, the other critical point at x equals 2, notice we have a sign change from negative to positive, and this makes a local minimum. So by the first derivative test here, we have a local minimum at x equals 2. Now, notice these two sentences I wrote slightly different, but these are the two main acceptable ways that you could explain why you have a local maximum or a local minimum. Now, before we move on, there is a shortcut to filling out this sign chart. You don't have to plug in all these numbers directly. Sometimes you could do this in a real sneaky way. So what I like to do for questions like this, if it's an option, is I look at f prime of x, which is this function here. It's a quadratic, and I know when I see a 3x squared that this is going to be a smiling quadratic. And since we have roots at 0 and 2, and this is a smiling quadratic, notice this would be a graph of f prime of x. Okay, so this is just a rough sketch of f prime, but notice the y values of f prime are above the x-axis, so they're positive, then they go under the x-axis, so they go negative, and then they go back over positive. And that's a fast way to record the sign chart, that it goes from plus to minus to plus. So for this next question here, f prime of x, we're going to use the chain rule. So we're going to have 3 times, we have x squared minus 4 to the 3 minus 1 is 2, but then don't forget we have to multiply by the derivative of the inside, which is 2x. So in simplified form here, this is going to be 6x, and then we have x squared minus 4 squared. So for this particular question here, we're going to set each factor equal to 0. We have 6x is equal to 0, and then we have x squared minus 4 squared is equal to 0. Now for this one, we're going to have x equals 0 as our first critical point. But now, to solve for this, we're just really looking for what is x squared minus 4 equal to 0, which is going to occur at x equals plus or minus 2. So when we make our sign chart for f prime, we're going to mark it at -2, 0, and +2. Now, one thing I want to point out, that there's a very dangerous bear trap in this question. So what I always look out for is that anytime I have a square factor or any even power factor attached to my binomial here, this tells me that this term, no matter what I plug in for x, is going to be always positive, or it's going to be equal to 0. But we never plug in the actual critical point, so we don't have to worry about this thing equaling 0. Now, how does that actually help us? Well, when we want to fill out the sign chart, if this part of the derivative is always positive, that means we only need to plug in the x values to the 6 times x component, and that's going to help us design the sign chart. So what I'm thinking here is if I want to plug in something like -3 on that first interval, if I plug in and do 6 times -3, that's -18. So I know it's going to start off negative here, our sign chart. Now, if I were to plug in something like -1, I would have 6 times -1, which is also negative. So notice here that I don't have a sign change. And once again, anytime you have a square factor or a factor raised to the 4th, any of the roots that come out of the square factor, like plus or minus 2, there's not going to be a sign change around those particular roots. So that's just a common trap, is that when students do these, they write minus and then they just assume it alternates and they write minus, plus, minus, plus. But you just have to be careful when you do these. So now we have f prime of 1, and if we plug in 1 here, remember this one is always positive, so I have a positive times, and then we have 6 times 1 is positive, so this is going to switch to a plus sign here. And then if we were to plug in 3, we have 6 times 3 is positive, and if we plug anything in here, this is positive, and a positive times a positive is positive. So this is our sign chart for f prime of x, but now the behavior of f is that f is decreasing from -infinity to -2. It's decreasing from -2 to 0, increasing from 0 to 2, and then increasing from 2 to infinity. And if we look at this graph here, you could see that this captures all of it. Notice the only local extreme value we have is we have a local minimum at 0, which is indicated by the sign chart. Notice we have a sign change from negative to positive at x equals 0. Now another scenario we could run into is we could be working with the e to the x exponential function here. Now for this one, we're going to have to use the product rule. So if you need to, you could go ahead and write u equals and v equals, and then we could find u prime is 2x minus 2, and that v prime is equal to e to the x. So now when we apply the product rule, remember we have u times v prime, so we're going to have x squared minus 2x times e to the x, plus, and then we're going to have 2x minus 2 times e to the x. So we have this here. And now to make life simple, what we're going to do is we're going to factor out e to the x. And then this is going to make x squared minus 2x, and then we're going to have plus 2x minus 2. And notice these terms here are going to cancel, so our simplified f prime is going to be e to the x, and we're going to have times x squared minus 2. Now if we set f prime of x equal to 0, f prime of x equals 0 when one thing to be mindful of here is that e to the x as a function here, this function is always positive. This function never reaches 0. It's always positive. So this is just something to be mindful of when we eventually make our sign chart. However, we can set x squared minus 2 equal to 0. And this is going to be true when x squared is equal to 2. And if we take the square root of both sides, this is true when x equals plus or minus the square root of 2. So when we make our sign chart for f prime, we're going to mark it at negative root 2 and positive root 2. Now we could use that nice trick for this. If we just focus on the x squared minus 2 piece here, and we think about what does that graph look like, well, we have roots at negative root 2 and positive root 2. And notice that if we look at this, this is a positive x squared, which means it's a smiling parabola. And this parabola starts off positive, goes negative, and then switches back to positive. And since this piece is always positive, we could kind of ignore this when we're making our sign chart, because what we have is to the left of negative root 2, we have this is positive times a positive, which makes this interval here from negative infinity to negative root 2 positive. Between the roots, negative root 2 and root 2, the x squared minus 2 component is negative, so we have a positive times a negative is negative, and then to the right of root 2, the parabola is positive, so we have a positive times a positive is positive. If need be, you could just plug in numbers. Just know, if you didn't just want to visualize the graph, you could do something like f prime of 0 equals, and you have e to the 0 times 0 minus 2 is negative 2, and then 1 times negative 2 is negative. So you could plug in numbers here, but I do like to just visualize what this looks like, and just it helps you fill out the sign chart really fast. So now what is the behavior of f? Well, f is going to start off increasing from negative infinity to negative root 2. Then it's going to decrease from negative root 2 to root 2, and then it's going to increase again. And if we look at this graph here, notice the function starts off increasing. This is about the location of negative root 2. This would be the location of positive root 2. And notice we have a sign change from plus to minus. That makes a local maximum here. And then we have a local minimum at positive root 2 when the derivative or slope changes from negative to positive. Now for question 4, we have a trig function attached to e to the x. And for these questions, it's really the pre-calculus that's going to make these questions more difficult, because the calculus itself is fairly straightforward, but it's all the extra math that you have to do that's going to make it tricky. So for something like this, we have to do the product rule. So the derivative of e to the x is e to the x, and we have times cosine x, plus, and then we're going to have e to the x times the derivative of cosine is negative sine x. And then if we factor this, f prime of x equals e to the x times cosine x minus sine x. So now this component, once again, e to the x is always positive. So when we look for our roots in a moment, we just have to keep that in mind. F prime of x is going to equal 0 strictly when the second factor equals 0, when cosine x minus sine x equals 0. But now we could do a little trigonometry here. This is going to be true when cosine x is equal to sine x, and if we divide both sides by cosine, we're really solving for when is 1 equal to sine over cosine makes tangent x. Be mindful the domain was restricted from 0 to 2 pi. So when we make our sign chart for f prime in a moment, we don't have arrows at either end. We're going to start it at 0 and we're going to stop it at 2 pi. So now what we have to think of here to find our critical points is we want to think about when is tangent equal to 1. Well, we write out the ASTC. Remember, all the trig functions are positive in quadrant 1, just sine and its reciprocal in quadrant 2, tangent and its reciprocal are positive in quadrant 3, and cosine and its reciprocal are positive in quadrant 4. So the first time in quadrant 1 tangent equals 1 is when x equals pi over 4 radians, also known as 45 degrees, and that's a quadrant 1 answer. But now, what's the actual angle in quadrant 3? Well, then our reference angle would be pi over 4 radians, or 45 degrees. And if we go 45 degrees into quadrant 3, from standard position, that's the same thing as going 180 plus 45, which is 225 degrees. And to get from 45 to 225, that's times 5. So we could also say our second solution here is 5 pi over 4 radians. And this is from 0 to 2 pi. So now I would mark this off at pi over 4 and at 5 pi over 4. Now, there's a few ways of going forward here, but what we could do is we could plug in values on each interval. And let's say for the first interval, once again, pi over 4 is 45 degrees. I would probably want to, if I'm doing this in my head, I would probably plug in 30 degrees, which is pi over 6 radians. So at f prime of pi over 6, like this is what I'm thinking about, e to the x is always positive. So I could say e to the pi over 6, but that's not going to matter because this is always positive. I only care about the sign. And now cosine of pi over 6 is radical 3 over 2, minus sine of pi over 6 is a half. So this is always positive, e to a power, and then radical 3 halves minus 1 half is going to be positive because radical 3 is bigger than 1. So that tells us on the first interval we have something, our f prime is positive, which makes sense because this graph starts off increasing. Now between pi over 4 and 5 pi over 4, this is from 45 degrees to 225 degrees. I would prefer to plug in 90 degrees, also known as pi over 2 radians. And the reason being is that it's going to make cosine equal to 0 and sine equal to 1. So we have e to the pi over 2 times cosine pi over 2 is 0 minus sine pi over 2 is 1. So now we have a positive times negative 1, and that's going to go negative, which makes sense because now the curve starts to decrease. And then from 225 degrees to 360 degrees, I'd prefer to plug in 270 degrees, which is this angle here just going south. And that corresponds to 3 pi over 2 radians. So that's what I would plug in. And we'd have e to the 3 pi over 2. And then we'd have times cosine 3 pi over 2 is 0. Sine 3 pi over 2 is negative 1. So minus 1 becomes plus 1. So I have a positive times a positive is now positive. So then from here we could describe the behavior of f. F is increasing, then decreasing from pi over 4 to 5 pi over 4, then it increases again. So we have a local maximum at pi over 4 and a local minimum at 5 pi over 4. All right, for the last question here, this is what I like to call the sneaky scenario. And for this one, what I recommend you do is you find the domain of the function first. So if we look at f of x in an alternate format here, this we could call x to the 2/3 over, and then we have x minus 5 to the 1/3 power. So just know there is no restriction on what we could take the cube root of and square. So there's no problem up top. However, the bottom, we cannot take the cube root of 0 on bottom because then we would be dividing by 0, which would be a problem. So x is not going to be equal to 5, and we have a vertical asymptote at x equals 5 because there's no way to cancel that out with anything on top. And you can see by the graph here that's very clear that at x equals 5 we have a vertical asymptote. Now the reason why I'm bringing this up now is that when we find the derivative in a moment, notice in this graph here we have a sharp turn. So the critical point that we're going to be finding from this function f of x is going to be the sharp turn kind where f prime does not exist at that location, giving us the sharp turn. So now let's go ahead and find the actual derivative. So we're going to have f prime of x, and let's say we want to use the product rule. So we'll call this will be our u term, and this will be our v term. So we're going to have 2/3 x to the negative 1/3 times x minus 5 to the negative 1/3, and then we're going to add, we have x to the 2/3 times the derivative. So to do this derivative, we're going to do the power rule. We have negative 1/3 coming down, and then we have x minus 5 to the negative 1/3 minus 1, which is negative 4/3. So what makes this question particularly awful is the algebra. This is definitely the most annoying part of these questions. And these are the kind of questions I get the most complaints from students, because just the amount of algebra we have to do is going to be crazy. So this is 2 over, we have a 3 here, and then we could call this x to the 1/3 power on bottom, and we have x minus 5 to the 1/3 power. And now here we could tack on a minus. So we're going to write minus, and I'm going to leave a little space. We're going to have x to the 2/3 on top. And then we have a 3 in the denominator from the 1/3. And then we're going to have x minus 5 to the 4/3 on bottom. So what I want to do for this question before we start finding critical points is I want common denominators. So notice they both have a denominator of 3, which is good. But this second fraction is missing an x to the 1/3. So we can multiply by x to the 1/3 over x to the 1/3. And now the x to the 1/3 matches. But notice here that this first fraction is only x minus 5 to the 1/3 versus this x minus 5 to the 4/3. So if we multiply this fraction by x minus 5 to the 1 to the first power, or we could think of it as to the 3 over 3, then that's going to make these denominators match directly. Because notice when I multiply these two terms with the same base, I add the exponents, and I'm going to get x minus 5 to the 4/3. Now just be mindful here when we do x to the 2/3 times x to the 1/3, when you add 2/3 plus 1/3, that's going to make 3/3, or x, and that's going to give you x to the first power. So now that we're at this stage here, what we could do with this is we could combine these fractions because now they have the same denominator. Now at this step here, we just simplify a little bit more, and now we're going to have x minus 10 over, and we have this denominator here. So now let's find the critical points. Now there's two types of critical points. We have to be very careful here. The most common critical point that students look for is when the derivative is 0. And if your derivative is in fraction form, a fraction is equal to 0 when the numerator is equal to 0 and the denominator is non-zero. So in this case, we say f prime is 0 when just the numerator x minus 10 equals 0. And this is going to give us x equals 10 as one of our critical points. Now, what we also have to consider is the sneaky critical point when f prime of x is undefined. So we have f prime of x is undefined, and this is going to occur for two values of x. And this might just be obvious, it may jump out at you, but when the denominator is 0. So that's going to be true when x equals 0, or we're going to have x equals 5. That's the other one here that would make the denominator equal to 0. But one thing to be very, 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 very careful of is that the 5 is something that we have to discard when we're talking about critical points. This one here counts as a critical point. However, x equals 5 does not count as a critical point because x equals 5 is not in the domain of f of x. So I kept this question for the last question because it's one of the sneakiest questions that you could run into with local extrema. But just know the sneaky critical point is where f prime is undefined, but you have to make sure that value of x is in the domain of the original function. Now, if we look at the original graph real quick of f of x, once again, x equals 5 is not in the domain of the function because we have a vertical asymptote here. So now we're ready to make our sign chart. We're making a sign chart for f prime, but what we're going to do is we're going to record the critical points. So we have a critical point at x equals 10. That's going to be way out here. And then at x equals 0, we have another critical point. But one thing I like to include here, at x equals 5, this is not a critical point, but we have a vertical asymptote at x equals 5. So I still like to plug in values before and after, but I just want to be very careful here. Notice at x equals 10, we had a 0 slope, and at x equals 0, the slope was undefined. That's why at x equals 0, we once again have the sharp turn. So now what we do is we plug in values to the derivative before 0. So if we look here, I would just pay attention to this part here, that if you plug in something like -1, so this is more of like a mental math thought process here, that if we plug in something like f prime of -1, notice I'm going to have a negative here times this term, I'm just going to point out, is always positive, except at x equals 5, but we're not going to plug in 5. So this is always positive. So if I plug in to the derivative here, I have negative 1, so we're plugging in negative 1. Negative 1 minus 10 is negative. The cube root of negative 1 is also negative, so a negative over negative goes positive. So that's why here f prime is going to be positive from negative infinity to 0. And notice the graph does start off by increasing. Now from 0 to 5, I would plug in 1. So far we had this one was positive. F prime of 1, if you plug in, now I have 1 minus 10 is negative. The cube root of 1 is positive. This is always positive, so I have a negative over a positive, which is negative. So notice I have a sign change from plus to minus. So the behavior of f, we're going from increasing to decreasing. So we have a local maximum at x equals 0. Now I'm going to plug in something between 5 and 10. So let's plug in something like 6. And so this one here was negative. If we plug in 6, now we look at this, 6 minus 10 is negative. And then we have the cube root of 6 is positive, and a negative over a positive times something always positive is going to work out negative. And notice here, our function is decreasing up until this location. Now, right after 10, so this was also negative. Let's say we plug in x equals 11. So we're going to plug in x equals 11 to f prime. Now we have 11 minus 10 is positive. The cube root of 11 is positive, and this is positive. So we're going to switch back to positive here. So the behavior of f goes from decreasing to increasing at x equals 10, giving us a local minimum.